Now that you're familiar with the size of the components and the brute force engineering involved, let's go through the startup procedure. First, turn on the rectifier filaments so that the ambient temperature in the rectifier cubicle will reach 90 degrees. Next, turn on the filaments of the 8 tubes in the 2 modulators and the 12 tubes in the 3 power amplifiers. Then, set the circuit breakers in the Y position for the power transformer primaries. Proceed through the following checklist. 1. Check water flow through each 898 jacket. 2. Turn on all the 898 filaments and observe each filament strand through dark welding goggles. 3. Check bias voltage to each power amplifier for 3,000 volts. 4. Apply plate voltage to power amplifiers and modulators. 5. Switch the 50,000 watt transmitter to its function as a driver for the 500,000 watt amplifiers and check tuning and coupling on each of the 3 power amplifiers. 6. Change the primary breakers to the delta settings. 7. Increase the modulation to normal levels. 8. Recheck tuning and get a great thrill in dipping the plate currents to 100 amperes. The total output of the 3 power amplifiers is fed to a harmonic filter, then into a 100-ohm air dielectric coaxial line. The RMS unmodulated radio frequency current at this point is 70.7 amperes. The 800-foot transmission line enters the coupling house at the base of the 831-foot tower. It is matched through an L network to the 390-ohm base impedance of the tower. The tower base current of 35.7 amperes produces 500,000 watts output, which creates a field intensity of over 6 volts per meter at 1 mile from the tower. The half millivolt per meter contour was about 300 miles from the station. The tower base insulator supports 110 tons of steel, plus 340 tons of vertical component of guy wire tension, for a total of 450 tons. Notice the ball gap for lightning protection and the rifle barrel photoelectric cell to trip the high-speed breaker to deionize the gap. This was necessary because the transmitter power was sufficient to sustain the arc once the gap was ionized. Everyone is aware of the power of lightning. Here we see the dramatic effect of a direct hit on the steel ball on the flagpole atop the tower. Various measurements were made to determine the amplitude of the lightning current. WLW engineers measured currents as high as 40,000 amperes. It first went on the air as a commercial station on April 17, 1934, and operated full-time until March 1, 1939, when Senator Burton Wheeler of Montana railroaded a resolution through the Senate limiting the power of commercial U.S. broadcast stations to 50,000 watts. This was done on behalf of Ed Craney, one of his constituents, who owned and operated a 250-watt local station and wanted to obtain a license to operate with 50,000 watts on WLW's frequency. WLW appealed, and it was decided that it could retain its clear channel status. However, from the time of that 1939 Senate resolution onward, the 500,000-watt transmitter was limited to experimental, non-commercial operation from midnight to 2 a.m. And so, at midnight, the WLW studio announcer would say, "We ask your indulgence a moment while we make transmitter adjustments to operate with 500,000 watts under the experimental call letters of W8XO. 1 moment, please." And each night, the first program broadcast was the well-known Moon River, whose familiar opening poem began, "Moon River, a lazy stream of dreams, twined in the hair of night." Finally, in late 1943, experimental authorization expired, and this great pioneering effort in broadcast transmitter technology ended. By 1944, Mr. Crosley lost interest in broadcasting and turned his attention to other pursuits, such as the manufacture of appliances, production of small automobiles, and the Cincinnati Reds baseball team. In 1945, he sold the broadcasting and manufacturing companies to Avco Corporation, while retaining his ownership of the automobile plant and the baseball team. During and beyond the time of WLW's 500,000-watt operation, efforts for the use of higher power for commercial broadcasting continued. The licensees of a number of Class 1A clear channel stations organized to perpetuate the concept of high-power, clear-channel skywave service to the entire population. This map, prepared in 1960, shows what the daytime coverage of WLW would be with a proposed power of 1 million watts. The three types of daytime ground wave service are grades A, B, and C, as shown by the red, orange, and yellow areas. During the daytime hours, these services are limited by rural man-made noise, urban man-made noise, and adjacent channel interference. For grade A service in rural areas, a ground wave signal of 1.5 millivolts per meter is required. For urban service, the signal must be sufficiently strong to override the man-made noise and serve 90% or more of the population. For grade B service, the ground wave signal of a 0.5 millivolt per meter is required, and in urban areas, 70% of the population would be served. For grade C service, a ground wave signal of 1/10 of a millivolt per meter is required. In urban areas, this would reach 50% of the population. The white areas within the B and C contours indicate loss due to adjacent channel interference. For comparison, here's the 50,000-watt coverage of WLW using the same criteria for the A, B, and C contours. It's interesting to note that the major urban areas of Columbus and Indianapolis are well within the grade A contour, yet only 70% of their population can be served because of the interference from urban man-made noise. One of the main arguments for higher power was to offset the substantial increase in man-made noise. Electrical appliances are the main cause of this interference. To illustrate this, notice the rapid increase in electrical energy consumption between 1938 and 1958. Since most electric appliances generate some form of electrical noise, the result was an increase in interference to AM radio reception. Note that rural electric energy consumption increased far more rapidly than urban consumption. The black areas on this map indicate where AM nighttime ground wave reception was available as of 1957. The white areas are locations where no nighttime ground wave reception was available. The people living in these white areas depended entirely upon the skywave service from clear channel stations for their nighttime reception. It's interesting to note that even today, the white areas remain virtually unchanged. Over 75% of the population residing in the white areas lies east of the Mississippi River. In 1946, the FCC initiated hearings to determine the future of AM broadcasting, particularly focusing on clear channel stations. These hearings, designated as Docket 6741, would drag on for many years. In 1960, the FCC reopened Docket 6741 and proposed assigning additional stations to some of the channels. WLW joined with other clear channel stations in opposing the plan. In addition, they presented detailed exhibits showing that a better method of providing nighttime reception to the white areas would be to maintain the clear channel concept and permit them to increase power to 1 million watts. This would be the average nighttime coverage of WLW when operating with a power of 1 million watts. The previously mentioned ground wave service remains nearly the same as the daytime map, except for the distortion or selective fading zone, which limits reception approximately 100 miles from the station, because the ground wave and the sky wave are nearly equal in intensity. This area is represented by the yellow ring covering parts of Ohio, Indiana, and Kentucky. The nighttime coverage is represented by types D, E, and F reception, as shown in the cross-hatched red, orange, and yellow areas. The D, or red area, represents the most reliable service expected to be available 90% or more of the nights of the year. The F, or yellow area, represents the least reliable service, expected to be available only 50% of the nights. Adjacent channel interference is also a factor, but is not shown on this map. The red area on this map shows how WLW, with a power of 1 million watts, could cover a substantial portion of the existing white area in the eastern part of the country. This coverage is based upon average atmospheric noise data. Nighttime atmospheric noise is the predominant limitation to skywave service. Atmospheric noise varies greatly with the seasons, being lowest in the winter months and highest in summer due to thunderstorm activity. The prediction of atmospheric noise was based on a report published by the International Telecommunications Union in Geneva. A portion of the data was gathered by WLW engineers who made continuous chart recordings of atmospheric noise for many years at a site near Cincinnati. Here we see the nighttime field intensities, which would be required in the summer to override atmospheric noise 50% or more of the time. Recall the map showing the proposed WLW nighttime coverage at 1 million watts. For comparison, this map shows the nighttime coverage at 50,000 watts. You'll notice that there is no red or D-grade service at this power. To illustrate how coverage varies with seasons, this map shows the predicted winter nighttime coverage. From this you can see why WLW, which had similar coverage with 500,000 watts, became known as the nation's station. In 1960, as convincing as the arguments in favor of high power on AM radio seemed to be, FM and television had become major factors, and AM radio no longer was the dominant communications medium. The FCC began to assign additional stations on some of the Clear Channel frequencies, and the long quest for high power for AM radio died. This program was researched and written by Clyde G. Haehnle and Edwin B. Dooley, both of whom were registered professional engineers in the state of Ohio. As engineering executives with Avco and Crosley Broadcasting, they worked extensively on the 500,000-watt engineering and the litigation aspects of the Clear Channel high-power proposals. I'm your narrator, Bill Myers.